All right. So the next part of electricity that we're going to look at is called electric potential difference. Another way of saying it is the voltage. All right. Now, the voltage or electric potential is the amount of energy required for each charge to move from one point to another in an electric field. Wow, that sounds complicated. But again, it comes down to the point I was talking about with current, is that we have a positive side or positives, and we have negatives. And what the voltage is all about is how much energy does it take to separate these two? And that's why it's called the difference, because you're taking them apart. What's the difference between them? The amount of energy it takes to push. It's like a spring, like I mentioned before. It's how hard did you have to pull on that spring to separate these two charges? Because again, when we release them, that energy is released and the negative travels towards the positive. So again, what you have, here's my wire over here again, is that we have charge moving through the wire, right? We have these charges, and Q, again, is the amount of charge in coulombs that flows through this wire. Now, the key here is that each charge has a certain amount of energy because it's been separated from the positives. So they each have delta E worth of energy. Each of these negatives, because they're pulled apart from the positives, has energy. And just like the spring analogy, every spring is different. So every charge is different in certain situations. All right. And so our voltage formula is we're looking at how much energy does each charge actually have. So the big difference here between voltage and current, and again, hopefully you've heard those words before, but I'm not assuming that you have, is that current is a measure of how many charges are going through this wire, where voltage is how powerful those charges are, how much energy each charge has. And so what can happen with electricity a lot of times, or what used to happen is, I don't know, it seemed like people were getting electrocuted when I was younger more often, which is a good thing that they're not. But what happens is that you'd hear these stories of somebody getting hit with 50,000 volts of energy, and they were surviving. And people would go like, wow, how'd they survive? Well, the key is the voltage, even though a charge is very powerful, 50,000 volts is a lot of energy for one charge. If there's only one charge, it's probably not going to kill you. But what can kill you is if the amperage is high, the current is high. If a lot of charges have hit you, say you have 1 million charges hit you and they're only worth 1 volt, well, that's 1 million volts going into your body, and that will kill you. Where if you just have one charge at 50,000, yeah, well, you're probably going to die too, but you have a chance of survival. So again, the key there is, what I'm trying to say is, voltage is how powerful your charges are, how much energy they have, where current is how many charges you have. Now, the interesting thing with voltage is, because it's the amount of energy that each charge has, it has to be regulated. And in Canada, when you plug something in, or all of our devices, our computers, our cell phones, speakers, TVs, anything you can think of, uses 120 volt charges. All right, so it's just how many they actually need, but the charges themselves are all 120 volts, except for high-powered equipment in our house, such as dryers, electric stoves, rather big items, will require probably 200, usually they're double, 240 volts of energy. But for the most part, everything in your house uses 120 volts. Now, one of the problems you can run into is if you travel. Is in Canada, we use 120 volts. United States, I believe, use 120 volts. But if you go over to Europe, some places only use, the plugs only have, say, 100 volts. So you can plug something in, and what happens is there's not enough energy, and the item won't work because the charges do not have enough energy to make your computer work, or whatever you might have. Or you get the opposite thing can happen. You could go to some place in Europe or say maybe Australia. I don't know. I can't remember. And the charges coming out of the plug might be 140 volts. So what happens is if you plug in your device, the energy or the charges going to your device are too powerful and they fry your device. I once went on a school trip to Poland, and that happened to people, that they plugged in their hairdryer, I think it was, and they fried the hairdryer within 2 seconds. So there is conversion plugs that you can use when you travel. You just have to be aware of that, that the voltage may be different coming out of the plugs if you're not in Canada or the US. All right, so again, voltage is how powerful each of our charges are. All right, so we get to example 1 here. How much energy does a light bulb use if it has 220 coulombs of charge passing through it with a potential difference, again, that's another word for voltage, of 120 volts? All right, so what we're looking for here is how much energy is being used. Now, this light bulb has a charge of 220 coulombs of use. So that's our Q value, 220 coulombs. The voltage or potential difference, again, they call it potential difference because it's potentially you're carrying these positive and negative charges apart, and they want to opposites attract, and they want to go towards each other. And that voltage is 120. All right, so again, looking at my formula, where I have V is equal to delta E divided by Q. All right, so let's see here. Oh, this time I know the voltage, so that's 120 volts. My delta E, that's what we're trying to find out, how much energy is being used up. And my Q here is 220. It's hard for me to draw twos on here. All right, again, I have something equaling a fraction. So I'm going to create a fraction equals a fraction. All right, so again, I'm going to cross multiply where I have that little red 1 times delta E. Well, that's going to equal delta E. And then I'm going to have 120 times 220. All right, well, I can figure that straight out. Just grab my calculator here, and big number, of course, and we get 26,400 joules of energy is used up by this light bulb. All right, so what else we got here? 120 volt charges flow through a light bulb again, operating on an electric current of 0.75 amps, and it's used for 5 minutes. How much energy does the light bulb use? All right, so again, we're trying to find energy here. So I like using blue here. So let's go with delta E. That's what we're trying to find out again, how much energy is passed through. All right, now the information we know. The voltage, again, it's 120, standard coming out of your plugs in your house, 120 volt charges. All right, now we also know the current. The current for this situation is 0.75 amps. All right, now the time, 5 minutes. Yikes, that's not good for us. Because again, not in standard units, got to be in seconds. So, well, there's 60 seconds in a minute. And so if I got 5 of them, 5 times 60 gives me 300 seconds. Okay, do we know anything else? That's it. All right, so let's check things out here. So again, I have my formula. V is equal to delta E divided by Q. All right, so I substitute in. Let's see here. I got, I'm going to have a bit of a problem here. I have the voltage. I want to find the energy, but I do not have my Q value. Yikes, okay. So here's what I'm going to do about that, is I have this other information. I do have the current. I do have the time. Now, the formula for earlier today, I have I is equal to Q divided by T. All right, so I do have the I, and I do have the T. So I can find the Q. And then once I find the Q, I can plug it in as formula. So we're going to have to do 2 steps here. All right. So again, my current here is 0.75 is equal to Q and divided by my time, which I now have my standard units of 300 seconds. All right, well, surprise, surprise, I have something equaling a fraction, so we'll go with a fraction equaling a fraction. We'll create that. And let's see here. I have cross multiply here. I have 1 times Q. That gives me Q. And then I can have my 0.75 times 300. And let's see, I multiply 0.75 times 300 and I get 2 something. Let's see here, 225 coulombs. All right, so now I do know how much charge I have. 225 coulombs. So now I can go back and again find the energy. So I had to just do an extra formula there. All right, so my voltage again was 120 volts. This is again why I write everything down on the side so I can easily access it, don't get lost. All right, so I got 120. Again, we're trying to figure out how much energy is flowing through. All right, my Q here is 225 coulombs. And look what we got here. Again, something equaling a fraction. So I'm going to create a fraction equaling a fraction. And let's see here. This time I've got my delta E times 1. Well, that's going to be delta E. And then I'm going to have 120 here times 225. And let's see, I multiply those two. Again, I'm going to get a huge number here, I imagine. And I do 27,000 joules of energy. So again, our voltage is how powerful our charges are, and our current talks about how many there are.